Good evening, everybody, and a warm welcome to you this evening who've ventured into the realm of radio astronomy on the weekend of a Platinum Jubilee. And also a welcome to all of you joining us on our YouTube channel in the future. Just a couple of points. One, apologies for the email link failing to arrive. I sent it out to all of you who requested after I notified on the group that I'd had some comment that the link wasn't out. I'm going to use a bulk mail client in the future so that we'll avoid those problems. So apologies for that. In August, we don't have a scheduled meeting, but I'm quite prepared to put something together if there's enough interest in members sharing results and details of their instrumentation. Excuse me. So just mail me personally on that point, and we'll see if anything. Let's see if we get enough to put a program together in August. In July next month, we've got Prof Madison joining us, and he spends his life down in the Antarctic, I think, collecting neutrinos to inform us about the cosmos. So that should be another very interesting evening. However, tonight we've got Leah, Professor Leah Morabito with us. And first of all, I just want to thank you for giving up your Friday evening and the local Jubilee party and the time, and to say thank you for the time you've put in to just prepare this for us. You are very welcome. Leah spent her time studying in the USA and in Europe and is currently at Durham University, beautiful campus. So without more words from me, our screens are yours, Leah.
Okay, thank you. Let me just share my slides. Okay, great. So, well, thank you very much for coming out this Friday evening. I mean, it's not very far to hop on Zoom, which is one of the nice things that's come out of this pandemic, is that we can connect with each other virtually like this. But thank you also for the invitation to talk. I'm always very excited to share my passion for science and my passion for radio astronomy in particular. And so the radio section of the BAA is actually a fantastic place for me to give a talk. So tonight I'm going to tell you about the International LOFAR Telescope and how high resolution radio observations can help us understand supermassive black holes. So there will be a little bit of technical things in here and a little bit of science. So hopefully everybody is happy no matter what you're more interested in. So first of all, thank you for celebrating the Jubilee weekend with a bit of radio astronomy. I went to a Jubilee party last night, and I've been having a very nice sunny day actually today, enjoying the Jubilee weekend, and it's great. And I hope that this fantastic weather continues all weekend. But thank you very much for coming out and listening to me tonight. So what we're going to talk about today. You might have seen this news article last year in August. Astronomers see galaxies in ultra high definition. So if you didn't miss it, if you did miss it, then you can go catch up on it later. But what we're going to cover essentially is these new ultra high definition images that we've made using the LOFAR telescope and how we made them. So by the end of the talk, you'll be able to go and tell all of your friends that you know exactly how these images were made and exactly why they're important and what we've learned from them. So there's more than just one result that's come out of this. And so we're going to cover a few of these. So these are new scientific results using the low frequency array, or LOFAR, and we'll get into what LOFAR is a little bit more in just a minute. But tonight we're going to talk about how advances in high resolution imaging with LOFAR have driven new science. And I just want to state at the beginning of this talk that this work has been a team effort in an international collaboration, And much of the work has been led by PhD students. So really a lot of the credit goes to them for, all of the hard work that they've put in. They're beginning their career in radio astronomy, but they still have done this, fantastic work to get to these new science results, and really they should be lauded for that. Okay, so here's a little outline of what we're going to cover today. So the first thing we'll do is just give a little bit of motivation. So what are the big open questions we want to answer? So just a brief introduction to galaxy evolution. We'll talk about how we made these images. So this will be kind of the technical section of the talk. We'll cover a little bit of radio interferometry basics, just because I understand that the audience can be a little bit broad. And so I want to make sure everyone is on the same page. We'll talk about the International LOFAR telescope specifically, and then cover these new advances that we've made in high resolution imaging. And then once we understand how these images are made, we'll talk about the new science that we've learned from these ultra high definition images that we've made. And I'll just wrap up with some ongoing work and future plans. Right. So some of you may have seen this movie before, but this is the Millennium simulation. And as we zoom in, we're going from the very large scale, and you can see, as we zoom in, you can see these beautiful filamentary structures, these nodes in these filaments where you have galaxy clusters, so clusters of galaxies that have maybe like a really massive galaxy at the center of the cluster surrounded by smaller satellite galaxies. And you can see that there's so much structure in the universe. And we see this structure in the universe, and we build simulations to try to understand how the universe actually formed. Because only by saying, okay, these are the laws of physics that we know are governing galaxy evolution, how galaxies are born, how they evolve, and then how they die eventually. By implementing those rules on how we think that the universe works, we can build simulations like this and then go out and match them to observations. So here we've zoomed into a galaxy cluster, and now we're going to zoom all the way back out and see our little fake universe here. And then the question is, how well does this match the real universe that we see? And next slide, right. So to check our understanding, we build cosmological simulations like the Millennium simulation, the video I just showed you, but also like the Eagle simulation, which is run at Durham University, where I'm based. And we see that the simple models can't explain observables. So by that, I mean, we go out and we do things like we count the number of galaxies that we see. So this plot here shows you the number of galaxies per volume of a certain stellar mass or size. So over here, you've got the small galaxies. Over here, you've got the big galaxies. You can see there are many more small galaxies than there are big galaxies. And this is the data. And so one of the things that we do is we say, okay, how does our simulation or how does our model match the data? And a simple model like lambda CDM, lambda cold dark matter, doesn't actually match it very well. So you can see that at this knee here of what we call the stellar mass function of galaxies, that we're actually matching the data quite well, but we're not matching it at all at the low mass end, and we're not matching it at all at the high mass end. So what's happening here? Well, from playing around with simulations, and for example, in Eagle, we've been able to better reproduce the data. And we've been able to do that at the low mass end for smaller galaxies by just introducing stellar feedback. So things like when stars have winds, these winds go out and they impact what's going on in the galaxy. And that's enough to make the simulation start to match the data. But at this high mass end, where you have these really massive galaxies, we found that we need to turn on what we call active galactic nuclei. And I say turn on in a very loose sense, because we turn them on. We know there's some form of energy deposit, but we don't know the details of how that works. So we know it's necessary to reproduce the observations, but we have no idea what the actual physical details are of what is actually happening there. So before we get into that, though, let me tell you what an active galactic nucleus is. So at the center of every massive galaxy, there is a supermassive black hole. And this is an artist's depiction of the very central part of a galaxy. So if you think of a galaxy as like the size of a football, then we're talking about something, a region of it that is smaller than the filler hole in the football. So this is a very, very tiny portion of the galaxy, but it can have a huge impact on the galaxy evolution. And we actually see correlations with the things like the black hole mass and global galactic properties, which is just mind-blowing when you think about the difference in size scales. So surrounding this supermassive black hole, you have what we call an accretion disk. And so this is when you have cold gas that's coming, it's being attracted by the gravitational potential of the black hole, so by the gravitational pull of the black hole. So the material comes down, it's trying to all cram onto the black hole at once, but it can't, and if it has some sort of angular momentum, so it's moving a little bit, it ends up setting up in a disk, like if you're watching water try to go down a drain, it can't all go down at the same time, and so it ends up swirling around the drain as it's trying to go in. So that's what an accretion disk is like. And so this is gets very bright because you're putting a lot of material in one place, it gets very hot, and then it emits in optical and UV wavelengths. Above that, you have some hot gas that emits an X-ray, and then around this entire region, you have what we call a dusty torus, because it is literally just dust, and it's in a torus shape around the accretion disk. The dust absorbs some of the heat that's coming off of the accretion disk, and then radiates in the infrared. So just like if you put on an infrared camera, you can see things that are warm. In about 10%, so about 10% of galaxies are active galactic nuclei, or have an active galactic nucleus, and about 10% of AGN have what we call radio jets, and these are jets of relativistic plasma that emit at radio wavelengths. So that is the picture of what we think is going on in an AGN. So we know that AGN are important because both from cosmological simulations and also from the fact that black hole properties correlate with galaxy properties, but there has to be some way to get the energy from the black hole all the way out into the galaxy. And this is the part where we're really kind of hazy. So we know that things happen on different scales. We know that you can have things like jets, you can have things like outflows or like winds, you can have just simple radiation. So if something is very bright and very hot and it's emitting light, that can go out and make other things warm, for example, and change the state of gas in the galaxy, which can then impact how it's forming stars and then how big it grows, for example. And so we know that these things can operate on all different kinds of scales, from the nuclear scale all the way up to the galaxy cluster scale. And you can see that jets, which I said before are radio jets, happen at all scales. And so they are a critical piece to understanding what is going on with moving energy from the black hole out into a galaxy to be able to shape its evolution. So the big questions that we're trying to answer here, really, by studying radio jets is, first of all, why are radio jets only seen in some AGN? What are the details of how jets impact galaxy evolution? And then also we see that in AGN that don't have jets, they do have some radio emission. So where is that radio emission coming from? And what part does that play in shaping galaxy evolution? Okay, so that's just a brief introduction to the motivation for why we want to, study radio with an eye to understanding what's going on in AGN. But let's just cover some of the technical stuff now. So just starting with radio interferometry basics. So hopefully some of you will recognize this array, which is in New Mexico. This is the Very Large Array. I actually got to spend a summer out there, which was really fantastic. I got to climb up in some of these dishes, which was super cool, and learn a lot about the array while I was doing some science. So there are 27 individual dishes in the array. They're all identical, and the reason that we have lots of dishes is because we want to increase resolution. So the resolution of a telescope is dependent on, if you just have one element, is just dependent on the size of that element. So if you have one single radio dish, your resolution is dependent on the wavelength over the diameter of that element. However, if you have an array of telescopes, what you can do is you're effectively simulating a much larger telescope. And now your resolution is dependent on the longest baseline between any pair of antennas in the array. So you're basically creating a bigger lens that is more sparsely sampled, because you can't completely fill the entire area here in this circle, but you can sample a lot of that area. So you're effectively building a bigger lens to get better resolution. And that's why we do radio interferometry. We move from single dish to using arrays of dishes. Just to show you some of the radio interferometers I've used. So as I mentioned, I spent a summer at the VLA. So here I am with a couple of the dishes you can see in the background. I've also used eMerlin, which is a UK array of telescopes. So this one is quite neat because they're all different kinds of dishes. And so we've pieced them together from previous radio telescopes or previous radar dishes and made them into a really nice array that can get quite high resolution. This here is the GMRT in India. And I was in the Air Force for 6 years after undergrad, but before I did my PhD, operating something that's not quite a radio interferometer, but very similar, called the passive detection system, which is strapped onto the this plane, the AWACS. So the cheeks here that you can see have essentially little radio antennas that sit there and listen for things that are emitting radio signals. And because the plane is moving, you get a line of sight, a direction of arrival from each thing that you're listening to, and then the plane moves a little bit, you get another one, and you can do a bit of basic triangulation. So not quite a radio interferometer, but a lot of the same technology goes into it. I mean, it is just radio antennas, just on a slightly different scale. Up here, this is the Meerkat telescope in South Africa. And then, of course, here is the focus of today's talk, which is LOFAR. So this is the low band antenna part of LOFAR. And here's me standing in a field of LOFAR antennas. So 3 of these telescopes have something in common. So they are all either pathfinders or precursors for the square kilometer array, which will be built both in South Africa, so where Meerkat is. So Meerkat will become part of the square kilometer array. And then there will also be a lower frequency component of this built in Australia. So these 3 telescopes are helping us figure out how to essentially do SKA science and handle SKA data before we start building the SKA. And so that's quite exciting, that all of this work will really help the next generation radio telescope that will come online actually quite soon. But for today, we're going to just focus on the low frequency array, or LOFAR. So LOFAR is a phased array that operates at about less than 200 megahertz. There's the low band antenna, which you can see here. This is just very simple dipole antennas like you might find in your own car. It's just there's loads and loads of them that are pieced together into what we call stations. And then there's the HBA, or high band antennas, and these operate just above the FM radio band. And so this one is a little more delicate. It's instead of just a wire, it's a little metal triangle here. And then you have another one over here, and then some orthogonal ones for the cross polarization, or the orthogonal polarization. And then it's held up by styrofoam and protected from the weather. So LOFAR has collections of these dipoles, and each collection of dipoles, collection of 96 dipoles, is what we call a station. And then these stations are effectively like the same as a dish in the VLA, right? So we have stations spread all across Europe, making LOFAR a very big interferometer indeed. And there's more than 110,000 dipoles at last count. We keep adding stations to the array, which is great because we keep improving the resolution. But then also, I never remember what the number of dipoles actually is because we keep adding stations to the array. So LOFAR has a very large fractional bandwidth, flexible spectral resolution, a wide instantaneous field of view. You can do multi-beaming with it, and it has flexible angular resolution. So basically, it's really super sensitive and it operates at low frequencies, which we'll come on to in just a minute. And because it has stations spread across such a wide geographic area, you can get really high resolution imaging out of it. Just to give you an idea of what one of these stations look like, in the center of the array in the Netherlands, this is what we call the SuperTerp, which is a collection of 6 stations. So here you can see one of the LBA stations, and then here you can see one part of the high band antenna stations. Right, so LOFAR looks a little bit different than this picture, right? So in practice, when we do interferometry, we're measuring voltages at each pair of telescopes, and then we use the known geometry of the system. We know which direction things are pointing. We know what the incoming wavefront, when it hits this telescope, how long of a delay there will be until it hits this telescope. And in LOFAR, which has no moving parts, rather than pointing our telescopes and then working out what this delay should be, we work out where we want to point and what the delay should be, and then we just introduce that delay in the signal path down here. So in interferometry in practice, you're just measuring voltages at telescopes, using the geometry of the system to pair everything up between pairs of antennas, and then you just make tens of thousands of measurements in an observation, and you take all of that information, you Fourier transform it into an image. So LOFAR is a software telescope because it does its pointing after it's observing, and it doesn't mechanically point, but electronically points. So why LOFAR? Why are low frequencies important? Why not just use the VLA, which operates at gigahertz frequencies? So radio emission comes from synchrotron radiation. So synchrotron radiation happens when you have a magnetic field, and then you have free electrons in that field, and those electrons spiral around the magnetic field line. And because they're changing direction, that's acceleration. And when you have acceleration, you can get radiation. So synchrotron radiation is free electrons spiraling in magnetic fields. Sources of synchrotron emission are, as I've mentioned already, radio jets and perhaps winds in AGN, but you can also get synchrotron emission from supernova remnants. So supernova remnants also have free electrons and magnetic fields. And so this is actually a really good way to trace star formation, because it's the most massive stars that go supernova, and the most massive stars are the shortest lived. So by tracking the supernova remnants, it's a really good way to actually kind of closely track what the star formation rate is in a galaxy. And in particular, low frequencies are important because synchrotron spectra, if you look at how bright something it is as a function of frequency, a synchrotron spectrum looks like this, and it's much brighter at low frequencies than at high frequencies. So that means that you can start looking at things that are fainter, because if you have the same flux limit for your, or brightness limit for your telescopes at different frequencies, you can see more things at lower frequencies that are fainter. You also can have low frequency absorption, and that's only seen at the low frequencies. So you wouldn't, for example, see this turnover in the spectrum where that radio emission is being absorbed by, perhaps some ionized gas that's along the line of sight. You wouldn't see this turnover if you're just observing with something like the Very Large Array. You can also see lower rest frequencies for high redshift sources. So things that are very far away, the spectrum gets redshifted as it comes towards us, which effectively moves this line over to the dashed line. And then you can see that with LOFAR, that's the only way we're ever going to be able to see anything that's happening at low frequencies. And then one interesting thing is that you also need low frequencies in combination with high frequencies to tell how old the radio emitting source is. So if you have just like a completely brand new, just born radio source, you'll get something like this red line. And then as it starts to age, then you start getting these curves. So this is 0 megayears, 25 megayears, 50, et cetera, et cetera. And you can see that you start to get this curvature, but at low frequencies, nothing much changes. And so to understand whether something starts out as the red line and then how far it's deviated from it, you have to know what that initial red line slope was. And you can see that at low frequencies, you're very, very close to what the initial slope of the red line was. And so you need to make measurements down here to be able to correctly interpret the curvature that you see at higher frequencies. And so LOFAR will be really crucial for doing this because you have to do it on spatially resolved scales because you need to compare like with like when you're comparing low and high frequencies. So it is important to observe at low frequencies, but there are challenges. So I thought I would just cover some of the main challenges that we have. So radio frequency interference, of course, is a problem for any radio astronomer at any band. So LOFAR, for example, operates around the FM radio band. So the LBA is just below, the HBA is just above because the FM band is unusable for us. The ionosphere is a huge problem. It requires directional dependent calibration. We'll come back to that in just a minute. The data volumes that we deal with are huge. So the data sets are an average of 4 to 20 terabytes per observation, which may or may not sound like a lot to you, but when you're trying to do calibration and imaging of Fourier transforms on 4 terabytes of data, it is a lot. And logistically, it's hard to just handle this data volume. Another thing is that we need precise timing information to understand when the signal is coming into one telescope relative to the other. The remote and international stations are all on individual clocks, and so we have to correct for any offsets between those clocks. We need calibrator sources that we know about, and we'll come on to this a little bit later. And that's something that we did not know a few years ago for LOFAR, and we have a much better handle on now. But also source characteristics can impact how well we can observe something at low frequencies, because this low frequency absorption can reduce your signal to noise if something is not as bright as you might expect it to be. So to just cover a couple of these challenges, so this shows you what the radio frequency interference is like, and this is mostly a solved problem. So this is the RFI occupancy of both the LBA and the HBA, and so this is the percentage of the signal that is due to RFI, and you can see these huge spikes in the data, and the HBA is even worse than the LBA. And these are non-astronomical signals. So these are noise that we have to get rid of. But Andre Offringa at Astron in the Netherlands has written an excellent automated flagger, which can also be adapted for other telescopes, which is great. That does a really good job of cleaning up the spectrum. So if your very weak signal is somewhere down here, you might actually have a chance of seeing it. I think one of the biggest problems for us, though, is the ionosphere. So if you imagine that you're laying at the bottom of a pool and trying to draw an accurate picture of a cloud, but someone's jumping in the pool next to you and the water is waving over you, you're going to have a hard time. And that's what the ionosphere does. So here is a 3x3 square field of view. It's the same part of the sky, 2 different observations and 2 different ionospheric conditions. The one on the left is in a poor ionospheric conditions, and the one on the right is in better ionospheric conditions. So these bright spots in the image, are actually very distant galaxies. They should not be moving. They should not be getting brighter. They should not be dimming in the time of this observation, which was, a very short, like hours kind of observation. But you can see that they're moving all over the place. Their shapes are even distorting somewhat, and that they're not all doing it in the same way. So it's not like every source shifts left or every source shifts right. Some of them are shifting left and some of them are shifting right. And that means that you have to correct your image in different ways in different directions. And that is a particularly nasty problem. And this is why observing at low frequencies is actually really, really hard. But we think it's a fairly solved problem. So this is the same part of sky, both before ionospheric correction and after ionospheric correction. So we essentially just divide the image up into different parts, and we find the calibration solutions or the corrections to the data in all of those different directions, and then we have to apply those corrections properly. So that then becomes a bookkeeping exercise. But it took us a while to develop the calibration strategies to do this, but you can see the results are just fantastic. So this is from the Fartimeter Sky Survey, which uses just the Dutch stations, but you can see the improvement in resolution is really incredible, and you can start to see a lot of really fantastic detail after you correct for the ionosphere. So speaking of the Fartimeter Sky Survey, this is an ongoing survey that we're conducting of the northern sky using the high band antenna, just the Dutch stations. So it has both a wide area component. We've had a couple of data releases. The most recent one was earlier this year. We're also looking at several fields where we have very, very good ancillary data at other wavelengths. We're going much, much deeper in those areas. For the wide area, we're cross-matching the radio to optical and IR, so we can get information on the host galaxies. So if you have a radio source, you need to also understand what its host properties are and what redshift it's at, and for that you need to make sure that you know which galaxy in the optical that radio belongs to. This is just a plot to show you how different surveys compare to each other. Here you have resolution versus frequency, and then everything has been scaled to the same sensitivity, assuming a typical synchrotron spectral index. So LOTS is down here at this frequency, and it covers only about half of the sky. So this is the sky coverage, how full the point is. But it's much more sensitive than quite a few of these other surveys. Which is really nice. For comparison, some optical telescopes that you might have heard of are pan-stars, and then the Hubble Space Telescope, the wide field camera, has this kind of resolution. So LOTS is really great. We're about, I think, a third to halfway through observing all of the data for the northern sky, and we already have over 200 science papers using LOTS data, which is really great. It's really taught us a lot about what's going on at low frequencies already. And so here's just a collection of images of galaxies that have radio emission from LOTS. You can see there's like really a beautiful diversity of sources. So we see things like AGN. So here's something where you have the galaxy in the center and it's making these very big jets. So these relativistic jets of plasma that then are very bright at radio frequencies. But we also see things like star-forming galaxies. And so this is the nearby Whirlpool galaxy in radio. And there's a lot of detail in these images, but out of the 4.4 million sources in the second data release that came out earlier this year, 95% of them are unresolved, which means 95% of them do not look like this. They just look like a blob. So something that looks like one of the images on this slide, you can look at, you can study, you can understand what's going on, you can see the different components. But if something just looks like a blob, what do you do? How do you know what's causing the radio emission? How do you know if it's something that looks like this star-forming galaxy down here, or if it's something that looks like something that has relativistic jets? So this is where the flexible angular resolution of LOFAR comes in. So LOFAR has stations spread all across Europe, but there are several different steps of resolution that you can think about. So if you use just the core stations, so the stations very, very close to the center of the array, in the Netherlands, you get some not very good resolution. If you use what we call the remote or short baselines, or just what we call the Dutch array, this is all the stations in the Netherlands, you get kind of 6 arcsecond resolution at about 150 megahertz. And this is where LOT sits, right? So this is what the LOFAR 2-meter sky survey uses, is just the Dutch stations at the moment. But if you expand out to use all of the stations in the array, then you can improve the resolution by a factor of 20. And then you can actually start getting better resolution than you can achieve with adaptive optics for ground-based optical telescopes, which is just fantastic. So I can tell you, 6 arcseconds, 20 times improvement, but that doesn't really give you a feeling for how good this improvement is. So if this image is made with the Dutch array, you can see that there's some shapes here, there's some color, but you can't really tell what it is. If I improve the resolution by a factor of 20, and this is what we're doing when we go from using the Dutch array to the international stations, you can immediately see it's my dogs in my backyard. So this is the kind of improvement in resolution that we're talking about when we're talking about high resolution imaging with LOFAR using the international stations. Extending to higher resolution has its challenges though. As I mentioned already, the data volume is a problem, the clocks are a problem, source characteristics are a problem, calibrators are a problem. And so the question becomes, how do we handle these challenges? So the first thing that we need to cover is how we correct the data. And to correct the data, we use calibrator sources, for which we have models, and then we find the necessary corrections to do this direction-dependent, correcting to make our data be error-free, as error-free as possible. So this is an observation of some galaxy, and you can see it's the background doesn't look very nice. There's a lot going on. And so what we do is we observe a source, which we know what it should look like, and we use this model to work out what we need to do to the data to make that source look like the model. And then we can calibrate it, and then we end up with something that's much nicer. So that's great, but what if you don't have models for your sources? Then you need to go out and you need to find sources that you can self-calibrate on. So essentially, find something that is bright enough and compact enough that you can actually do this. You can iterate, you can start with a simple model, do an iteration of calibration, make a better model, and then iterate to convergence. So if you can get to convergence, then you can create a model of a source, and then it can become a calibrator source. So to get an idea of what good calibrator sources were at low frequencies, we conducted the Long Baseline Calibrator Survey, which covers the entire northern sky for the HBA. This is the density of good calibrators in that sky, in the northern sky. And so we went out and we observed about 30,000 sources, and we found that there's about 1 good calibrator source per square degree, which it turns out is about what you need to be able to calibrate any direction in the sky. The Long Baseline Calibrator Survey includes things like quality indicators and metrics, but there was a paper out earlier this year that also did a little bit of science with the LBCS, and I encourage you to go check that out if you're interested in that. So once we have calibrators, we need to actually calibrate them. And calibration at high resolution has to handle lower signal to noise on long baselines. So the longer your baseline is, the higher your resolution, but then that means you, instead of looking at something that is a point source or a blob where all of the brightness is concentrated, you're looking at maybe multiple blobs that are each individually less bright. And so your signal to noise ratio goes down. And in order to compensate for that, you have to do something to get better signal to noise. And to get better signal to noise, you can increase your solution interval that you're finding calibration solutions to reduce your noise. So there's a technique called Fringe Fitting, which we've developed, that has been developed for high resolution radio imaging. And this solves for phase errors by also solving for delays and rates in addition to a phase offset. So I know that's quite technical. If you're interested in this kind of stuff, you can ask me about it afterwards. If you're not, then you can just understand that you don't actually need to know all the details of this to appreciate the rest of the talk. So for LOFAR, we can't actually use fringe fitting algorithms because until very, very recently, they've only been able to cope with non-dispersive phase delays. So phase errors where the phase is linear with frequency. But LOFAR, because it's dominated by the ionosphere, has a non-linear behavior of the phase errors, and this is a huge problem. And so we've gotten around this by just solving for the ionosphere directly, and then applying that to the data and then self-calibrating as normal. So we've developed a calibration strategy using LOFAR native tools. We correct for clock offsets. We solve directly for the ionosphere. We also use a trick where we combine all the core stations into a super station. And then this not only reduces our data volume, but helps anchor our calibration, our calibration of the data. The entire calibration strategy is written up into a pipeline that's available publicly on GitHub if you're interested in trying your hand out at LOFAR data reduction. And it's really built as an extension to the processing for the LOFAR 2-meter sky survey for reasons that will become apparent at the end of the talk. So the key elements here are that we solve directly for the ionosphere, and that also we combine the core stations to help the calibration by creating a super single, really sensitive station in the array, and it helps reduce the data volume. So how this works in practice, this is a typical LOFAR 2-meter sky survey observation, but it could be any observation that LOFAR has made in the sky. Our field of view is limited to a 1.25 degree radius, just because of the station beams and by smearing. But that gives us a field of view of about 5 degrees squared, which is about 25 to 30 times larger than the size of the moon on the sky. So the first thing that we do is we pick the best calibrator source from the long baseline calibrator survey, and we solve for the ionosphere on that. And then we can get a good image of our source there. So we calibrate, we self-calibrate until convergence. We get the good solutions for that direction for that particular source. And then we transfer those solutions to other sources in the field. So we can't image the entire field all at once very easily. And so what we do is we take little bits of the data that are in different directions, and we do postage stamp imaging and calibration of just individual sources. And so you can see that we start to see more structure in these sources. And what that looks like when you propagate these solutions around the field is that all of a sudden you go from blobs in the sky, and this is real data from that field. You go from blobs in the sky using just the Dutch array to being able to see all of the detail of what's going on in these sources, which is just absolutely fantastic. And over here is just to show you a demonstration of why it is so important to get this resolution, to understand how radio jets and radio things that produce radio emission are impacting, might be impacting a galaxy's evolution. So this is the optical galaxy. If you have just an image with the LOFAR Dutch stations, this orangey yellow blob is the radio emission. You can't tell what's going on. But when you image with the international stations, immediately you can see all of the fine detail of what's happening on galaxy scales. And this is really critical to being able to understand how this radio emission in these jets are interacting with what's going on with the stars that are generating the light in the optical band. So this kind of resolution is great for enabling science. So with this kind of resolving power, we can study these jets of relativistic plasma that are launched on both large scales and small scales. We can look at star formation in nearby galaxies. There was a special issue in Astronomy and Astrophysics with now 11 new articles that was published in January of 2022. And this more than doubled the number of scientific results using the LOFAR full international array, because standard operations up and have typically used just the Dutch stations. And I'd just like again to stress that most of these papers were led by earlier career researchers, so mostly PhD students and a couple of postdocs. Just to give you a little brief highlight of some of these new results. So Roland Timmerman, who's a PhD student at Leiden University in the Netherlands, looked at the origin of these ring structures that you see here in this galaxy that's called Hercules A. And by comparing the LOFAR data with images at higher frequencies, he was able to work out that these rings are actually consistent with the supermassive black hole at the center here turning off and on. So it turns on and it starts a jet, and then it turns off and the jet kind of turns off, and then it turns on again. And so this intermittent activity that you get is likely what's causing these rings here. Going to smaller scale jets, Pranav Kukredi, who's a PhD student at the University of Groningen, looked at these new jets that are located in the center of this galaxy, but this galaxy also hosts very old jets. So these old jets here are about 13 million years old, and the new jets that he sees here with LOFAR are 150,000 years old only. And so by using this, and again, coupling that with high resolution imaging at high frequencies, he was able to work out that actually you can see this turnover in the spectra, which implies that there's some interaction with the interstellar medium that's absorbing some of the radio emission from these jets. Moving from looking at AGN to looking at star formation, Naim Ramirez Olivencia looked at the nuclear emission in this pair of merging galaxies. And so this is the optical image with the orange is the radio overlaid. And here you can see there's this outflow from the center of this galaxy. And so the LOFAR images here, the new ones that she's made with the full international array, have shown that this diffuse emission in the outflow is likely powered by a starburst and not an AGN, although there is an AGN over here that could have possibly triggered this the star forming outflow, starburst outflow, which is quite interesting. So all of those results have been with the high band antenna, but Christian Grunewald has been looking at jets in very bright radio galaxies. So these very bright radio jets in AGN at the lower frequencies with the low band antenna. And actually he broke the record for the highest resolution images ever made below 100 megahertz, which I was very, very happy to hear, because I was the record holder when he broke it, but I was so happy that he did this, because I mean, he's just done phenomenal work looking at these galaxies. It's just incredible that he can get this kind of resolution at such low frequencies. So by doing this, you can actually start to really do some very critical work studying the jet ages and the conditions of the radio jets in these sources. A PhD student at Leiden, Fritz Sveyen, has been imaging the complete 5-degree square field of view for one of the LOFAR 2-meter sky survey deep fields. This was published this year in Nature Astronomy. So from an 8-hour observation, he made an image that is about 7 billion pixels, and that is not like the postage stamp imaging I was talking before, but imaging the full field of view, which is much more difficult, much more computationally challenging. Took about 250,000 CPU hours, but I mean, just really, really incredible results. You can actually go online at this link, and you can see the imaging of the complete 5-degree squared field of view. So here is compared with the LOFAR 2-meter sky survey 6 arcsecond resolution image with just the Dutch array. And then here's Fritz's 7 billion pixel image, which you can't see anything in because it's so high resolution that you just can't see the sources. But if you go and play on the website, you will be able to zoom in and you can look at all of the details and all of these sources. It's very, very cool. And I'll just mention that LOFAR has a sliding scale for resolution. So we talked about the Fartimeter Sky Survey using just the Dutch stations, and then we jumped to 20 times improvement using all of the international stations. But you can actually just image with some of the international stations and get slightly better resolution than with just the Dutch stations. But this here is less computationally expensive than doing, the full imaging at high resolution. But you can see that we're still improving. We're still improving our images of these sources, improving our knowledge of these sources, and then also getting an idea of what's happening at intermediate scales. So for this, for example, for this galaxy, you can see here that we have such good resolution that this very diffuse low surface brightness stuff is actually not detected in this high resolution image. So it's really great that we're starting to test now making these intermediate resolution images, which provide us additional information on what's going on in these radio sources. So I'll just wrap up in the next few minutes with some ongoing work. So I have talked a lot about the Fartimeter Sky Survey, and data release 2 that came out earlier this year has over 4 million sources. We have actually recorded the data with all the international stations, but we're still only processing them at the moment with 6 arcsecond resolution with the Dutch stations. So this is so eventually lots will cover the entire northern sky. The data release 2 is the black outlined areas here, just to give you an idea of how much of the sky that we've covered. But we're still just processing it at the more standard Dutch resolution. But one of the things that I'm working on as a UKRI Future Leaders Fellow at Durham University is post-processing the Fartimeter Sky Survey with the international stations, which will provide the first sub-arc-second northern sky survey. And to come back to this plot here, which shows you how radio surveys compare with each other in terms of resolution and frequency, that means that we move lots down to lots high resolution and into the regime where you're getting the same kind of resolution as the Hubble Space Telescope, which will just be phenomenal for trying to understand the interaction of all of this radio emission with whatever else is going on in these galaxies. So there are kind of 3 tiers to this. So we are working on the wide area. So starting in H-Atlas, imaging everything with postage stamp imaging that is brighter than a certain limit. I've been working with a postdoc at Hertfordshire, Johnny Pierce, and so here's a collection of the sources that he's been able to image. And then we're also working on the deep fields like the Lockman hole that Fritz worked on, and doing this initial imaging in these 3 special fields that we've picked, but then also going deeper in all of those fields. And then in the next couple of years, LOFAR will get an upgrade. And so we're going to have hopefully a LOFAR 2.0 ultra deep observation of the Euclid Deep Field North. So Euclid is a space satellite that's being launched and will provide really incredible data. And that'll be upcoming in the future. So I don't want to give a very detailed summary, but I do want to just kind of leave you with this take-home message that LOFAR is we're capable of performing sub-arc-second imaging with LOFAR. And this is already enabling new science, and I've shown you some of the highlights here today. And over the next few years, as we start surveying the northern sky by post-processing the Fartimeter Sky Survey, I hope we can expect more new and very exciting results. So I'll stop there and very happy to take questions.
Thank you very much. Absolutely incredible. It seems like with many aspects of radio astronomy, the advances in data processing enable the science to move forward very quickly. Yeah. I'd like to kick off with one question, and that is, I was fascinated at the beginning of your presentation on the steering, for the want of a better word, of the array by injecting known delay into the signal. What kind of time frame are we looking at here?
So that happens for the high band antenna. That happens in real time. The beamforming is done at the station level. But for the low band antenna, it happens at correlation. So the data is streamed to the correlator, where the correlator is just this supercomputer that puts all of the information together from all of the different stations. So the low band antenna array just actually observes and sends all of its data off. And then at the point where we put all of the data together is when we introduce the delays. Right.
I've got another question, which I'll ask, and then I'll open it up. And that is, obviously the timing is absolutely critical on this, and you have to make a correction because as I understood your presentation, each site has its own clock, as it were. How do you make that correction? How do you determine what the error is between the different stations?
So that's a really good question. Let me page back to this slide here. It's really tricky because you also have to deal with the ionosphere. So what we're doing is we're doing phase corrections. So when you're measuring voltages, you get amplitude and phase information, and you want to do phase correction. So the clock introduces a phase slope, and that phase slope is linear in frequency. But the ionosphere introduces a phase error, and that phase error is nonlinear in frequency. And so in practice, what we do is we observe very well-known, very bright, high signal-to-noise calibrator sources that we understand very well. We find the phase solutions, and then we fit in the phase solutions for a model that has both a linear slope and a non-linear slope. So we're fitting both directly for the ionosphere and also for the clock. And that's how we back out the clock values. But you have to do this on a very high signal to noise source, because otherwise your solutions will not be of good enough quality that you will be able to separate the effects of the ionosphere and the clock. And so there's only a few sources in the sky that are really bright enough to do this. And so we observe them just before or just after the end of every observation. So we have that information.
Right. Yes. Thank you. Thank you.
Yeah.
Are there any other questions? I'm sure there probably are, actually.
Yes, if I may ask a question, coming to this ionosphere thing. Mm-hmm. Obviously, you need to correct for all the effects that the ionosphere has. Now, the ionosphere obviously doesn't have a stationary situation.
Yeah.
So it is time dependent. What time scales are we talking about in changes of the ionosphere, which you have to take into account?
Yeah, so that really depends on the ionospheric conditions. And it depends also on the whether you're using the high band or the low band antenna. So the low band antenna, I mean, you could need to take things into account on scales of 5 to 10 seconds if the ionosphere is very bad. For the high band antenna, it's maybe more like 15 to 30 seconds if it's very bad. But in more stable conditions, then it's maybe on scales of like up to 3 to 5 minutes. And so the calibration strategy is a little bit iterative, where we find like the bulk correction for the ionosphere on shorter time scales, and then we can solve for residual effects that at maybe longer time scales.
I have a question. Obviously, with the detection that you are able to receive, as you mentioned, this is all synchrotron emission, correct?
Yeah. So you're dominated by synchrotron emission at these low frequencies. Yes.
So what you're actually observing are regions that have significant magnetic fields that allow for the emission to take place.
Mm-hmm. Yep.
Is there a possibility of observations with any type of line emissions? For example, I know that your upper frequency range doesn't quite get there, but there's the deuterium spin flip at 327 megahertz, which would make a very interesting line to observe in some of these observations. Is there a possibility that that could be achieved by some modification of the receiving antennas or the equipment?
So I think that one actually would be better for the square kilometer array because that will fall into its frequency coverage. But you can actually do spectroscopy with LOFAR. So people are very interested in trying to detect the hydrogen spin flip at 21 centimeters, but from very, very high redshifts. So for instance, from the epoch of reionization, the hydrogen emission from the spin flip of hydrogen is actually redshifted into the LOFAR frequency band. So people are trying to look for this. But you could also look for radio recombination lines from hydrogen-like atoms. So carbon, for example, carbon radio recombination lines. Although those are in absorption and they are actually much, much weaker. But there's been some work looking at carbon radio recombination lines both in our galaxy and in other galaxies as well.
I see.
Leah, you mentioned that there was an upgrade coming up for LOFAR.
Mm-hmm.
It doesn't sound as if that would be in terms of bandwidth, and I assume, are there more stations being added, or is this really down to the processing side of the system?
So it is back-end electronics, and I kind of glossed over this, but it actually does provide more bandwidth. So each station has 96 dipoles, and each HBA station has 96 dipoles, each LBA station has 96 dipoles, but in the international stations, so not the Dutch stations, but everything else, they have the back-end electronics to cope with all of those dipoles. But in the Netherlands, you have to make a choice, and you can only use 48 of them at a time. So by upgrading the back ends, you can either increase your bandwidth because you can actually start to use more dipoles at once, because it's not just the number of dipole, the bandwidth, the increased back-end electronics can either give you more dipoles or more bandwidth. It's basically the ability of like your data processing handling from the data flow from the station. So you can either use more dipoles or you can increase your bandwidth for the same number of dipoles. The really exciting thing about LOFAR 2.0 is that if you can increase your bandwidth or increase the number of dipoles that you're using, you can start to make simultaneous LBA and HBA observations, which we're not able to do at the moment. The LBA is far less sensitive than the HBA, and so it's harder, but is more impacted by the ionosphere because the ionosphere just gets worse at low frequencies. And so the really exciting thing there is that maybe if we do simultaneous observations, we can solve for the ionosphere and the HBA, apply that to the LBA, and then get better calibration with the LBA. So that, I think, is the most exciting thing about the LOFAR 2.0 upgrade.
If I may ask another question about the capabilities of LOFAR in general. What are the possibilities of LOFAR to look at transient phenomena? Obviously, a fast radio burst is one of the things that people are interested in. If I recall correctly, there has been some pulsar work with LOFAR successfully. But in general, what are the capabilities and, of course, limitations that you have for transient phenomena?
Yeah, so people do lots of transient work with LOFAR, actually. So both pulsars and FRBs are things that people look at. There's actually a group that's looking at re-imaging the low Fartimeter Sky Survey data, but on like 5-minute snapshots across a wide range of times, and then looking at difference imaging. LOFAR is a really great telescope for looking at transients, because if there's a trigger for something in the sky, so something unusual that you see at another wave band, LOFAR can actually point that in that direction very quickly, because you don't have to actually physically move the telescope. You can just say, I want to start looking here, and then you're introducing new phase delays in your signal path. So its responsiveness is really, really fantastic for looking at transient sources. The limitation is the amount of data, because and that's limited by what time resolution you need. So if you need very, very high time resolution, you just cannot store the data. And so what people have for LOFAR is what's called transient buffer boards. And so they observe, and the data goes into a buffer board, which is, you know, maybe a few minutes of data. That data is then searched very quickly with very, very efficient algorithms for any kind of signals. If there's no signal found, then it's dumped. And then if a signal is found, or something triggers the algorithm to say something weird is going on, then it saves that data so people can look at it later on. So I saw that someone had been trying to ask a question, but had some audio issues, and I couldn't hear what he was saying.
No, I can't hear Andrew.
Maybe he can type it in the chat.
Yeah, Andrew Thomas, I think, was wanting to ask a question.
Yeah, if you can, I've pulled up the chat, Andrew, so if you want to go ahead and type it out. Does anyone else have a question in the meantime while Andrew is typing?
Yeah, I have a kind of a question. Some of the other radio telescopes, the Green Bay telescope and so forth, have participated in SETI searches. Has LOFAR participated in any such collaborations?
Yeah, so Mike Garrett does some work on SETI, and his work is really nice, because whether or not he detects anything, then he does some really nice studies of star formation in nearby galaxies. So yeah, there has been some done with it. I don't know a lot of the details about it, but Mike Garrett is the person to look up for that.
Okay, am I completely unmuted?
Ah,
Yes.
I can hear you, Andrew.
Ah, that's better. Okay, technical problem with the connector. You showed a slide with 3 columns of increasing resolution.
Yes.
And mentioned one of the objects where there was a low surface brightness, which disappeared with increasing resolution. Now, is that you've processed out the low surface brightness object, or that the low surface brightness is an artifact at that resolution? I didn't quite understand what you were doing there.
Ah, right. Okay. Yeah, that's a really subtle point. So if you have if you increase your resolution, your sensitivity depends on the size of your resolution element. And so if your resolution element becomes smaller, then you have less flux density, or less brightness from the source in that resolution element, and it will eventually at some point just be below your detection limit. Does that make sense? And I think your microphone stopped working. But I saw a light of something go off. So I hope that answered your question. Can you give me a thumbs up? Okay, all right, good.
Okay, I had a question. You mentioned right at the outset that your biggest problem is RFI. How do you handle the FM stations?
So RFI is a huge problem, but I mean, I think the ionosphere is bigger, but RFI is a nasty problem. And we handle the FM band by just completely avoiding it. So the low band antenna only goes up to about 80 megahertz, and the high band antenna starts at 110. Although in practice, we don't use the very edges of either band because there's less sensitivity at the very edge, and also you can get some worse RFI at those edges. Yeah, we just have to completely avoid it.
Well, that high band is right in the aeronautical communications frequency range above 110. How do you handle these intermittent transmissions from, say, aircraft versus, say, a constant transmission from like an FM station that would be a constant signal?
Yeah, so if it's intermittent, it can be identified in the data because the astronomical signals that we're looking at are not intermittent. Unless you're looking at, someone asked a question about transients, but those have a very specific signature. And so something that is just like intermittent particularly at known frequencies for known transmitters, that can be filtered out. So the AO flagger that Andre Offringer wrote does a very good job at identifying signals like this because it searches across the entire bandwidth, but also across the entire time range. So you're basically looking at all of the data at once as a function of both frequency and time, and then looking for abnormalities or anything that's an outlier in that along either axis.
And then on some of the earlier work that you did, you mentioned you had been in the Air Force previously and worked on AWACS, and that was a passive detection that you were using. Could that provide something similar to like a synthetic aperture type detection with just passive, or like with radar where you can do synthetic aperture, or is it just simply a listening mode where you detect signals?
Yeah, the passive detection system is simply just a listening thing. There's no real synthetic aperture synthesis there at all. Yeah. But a lot of the components are the same as radio telescopes. I mean, it's an antenna. There's a feed horn goes into the system. It's signal analysis, but yeah, just passively listening.
Any future collaborations with the SKA when it comes online?
Yeah, so actually I'm quite involved in the Square Kilometer Array Regional Center. So I mean, yes, I'm excited to use the SKA as a scientist, but I'm also helping the regional centers get going. So the SKA is going to have such huge data rates that the data will be processed by the observatory and then handed off to what are called regional centers. And so these regional centers are in all of the partner countries, and they will provide computational resources for scientists to be able to play with and further, image or work with their data to get the science results that they want. And so there's a collection of us in the UK who are working towards building the UK Regional Center for the SKA. And so this will be the interface for scientists to access their data and to put, the final touches on it after it's been, bulk processed by the observatory. So yeah, my work with LOFAR has really put me in a position to be able to help out with that, because I've had to deal with a lot of the problems that the SKA will have to deal with, like large data volumes and how do you do your calibration efficiently and all of this kind of stuff.
How about correlations with the gravitational wave observations? Is there any possibility of any LOFAR observations with some of these events?
Ooh, yeah, that's a good question. I think someone had looked at that, but did not find any detections. But yeah, so Antonia Rawlinson did look at this, but she didn't find anything that was very exciting, and so I don't think it's published at all. Yep. Good question.
Leah, will the SKA have a better RFI environment? Andrew is asking.
Oh, so possibly, but it will cover some of the same frequency range, at least the SKA low, because that will go from 50 megahertz up to about 200 to 300. And so I think it won't have like necessarily a better RFI environment. But I think with the AO flagger, we know like, and with our experience with LOFAR, we kind of know what bits of the frequency band we need to avoid, and we also have a good handle on how to remove the rest of it.
Are there any more questions?
Right, so I see a question in the chat. By getting all of those data and images from an object, what can we do with those data? So that is a good question, and the answer is that it depends on the object. So you can use LOFAR for a lot of different things. You can use it to try to find out what kind of age the radioplasma is. You can use it to look for correlations between the radio emission and emission at other wavelengths. So like, is a radio jet propagating out and impacting the environment or impacting the galaxy that it's living in? Can you correlate where the radio jet is with, for example, the presence of ionized gas? So it really depends on the object specifically and what's going on in it. One of the really cool things you can do is you can actually identify AGN and separate them from star formation using these high resolution observations, which is something that I'm personally working on. Yeah, that's quite exciting. But it really depends on what you're trying to do with the data, what you can use the data for.
I guess this is all big stuff, Leah. Is there anything for amateurs to do in this area?
Yeah, actually, that's a great question. So there's something called LOFAR Galaxy Zoo. So I don't know if you've ever done any citizen science, but the Fartimeter Sky Survey, we, as I said, we're cross-matching it to the optical information, which is necessary so that we can understand, how far away these sources are, what kind of galaxies they live in, and understand, what might be generating the radio emission. But in 95% of the cases, we can do that very easily. We can do it in an automated way, but in like 5 to 10% of the cases, we can't. And 5 to 10% of 4.4 million is a lot of sources. And so we have a citizen science project with a nice tutorial where you can go and you can look at radio sources and say, I think this is the galaxy it lives in. And so definitely check that out. LOFAR Galaxy Zoo. If you Google it, you should find it. Yeah, absolutely, you can help out.
Sorry, that was LOFAR Galaxy Zoo.
Yep.
Yeah. Okay.
I can see if I can find a link and put it in the chat. Stop sharing. But yeah, and some of the people who have done LOFAR Galaxy Zoo, who have done a lot of classifications, have actually gotten to be co-authors on papers because of all of the work that they've helped out. So I've put the link in the chat, so you can go directly there and check it out.
Good, got it. Thank you very much.
You're welcome.
There was another link in your presentation.
Oh, yes.
Can you paste that into the chat as well?
I can indeed. Let me just open that. Yeah, that one is also quite cool to go and look at, the high resolution image. It's so hard to actually show anything from that image on the screen because it's just such a large image with such high resolution. that it's really hard to see unless it's like, you're sitting there and able to zoom in and play with it. So I've also put that in to the chat.
Oh,
so
thank
you.
you.
Go check that out. Yeah, of course. Who operates the LOFAR station in the UK at Chilbolton? So the STFC, the Science Technologies Research Council, and in conjunction with the Rutherford Appleton labs. You're welcome.
Are there any more questions? In which case I shall give a vote of thanks to Leah. That was just fantastic. Thank you so much. In the normal world, we'd be giving you a proper round of applause of appreciation.
I could see people clapping.
But the way things are, you had to look at our images and see everybody clapping. No, that was really good. Thank you so much. And as the next generation come online and results come out, we'll have you back in a year or two, Leah, to update us on the progress.
Sounds good.
Good. Thank you very much.
Yeah, thank you.
I shall say good night, and don't forget to save the chat if you want to hang on to those links. Good night, everybody, and enjoy the rest of this Jubilee weekend. Good night.
Good night.